Hi, I'm Thomas. Welcome back. Our topic is differentiation, and this is parametric differentiation example 2. Our requirement reads, find the equation of the normal at the point P where theta equals pi over 6 on the curve with parametric equations x equals 3 sine theta and y equals 5 cosine theta. Notice in our algorithm we're using t as our parameter. That's a general parameter. In this particular case, our parameter is theta. So wherever the algorithm references t, that will apply to theta in this particular example. Step 1, find a derivative of y with respect to, in our case, theta. So we're starting with the y equation. Y equals 5 cosine theta. The derivative of y with respect to theta is 5 times the derivative of cosine theta, which is negative sine theta, or negative 5 sine theta. Step 2, find derivative of x with respect to theta. Our x equation, x equals 3 sine theta. The derivative of x with respect to theta is 3 times the derivative of sine theta, which is cosine theta, or 3 cosine theta. Step 3, the derivative of y with respect to x is the derivative of y with respect to theta in the numerator. That calculation for us is negative 5 sine theta. And in the denominator, derivative of x with respect to theta. That for us is 3 cosine theta. Step 4, if required, which does apply in this case, calculate slope at given parameter value. Notice how our requirement relates to the normal, so we need to remember to take the negative inverse of the slope that we calculate. But let's begin with the slope calculation. At theta equals pi over 6, the derivative of y with respect to x is negative 5 sine of pi over 6 divided by 3 cosine pi over 6, and continuing, negative 5 times sine of pi over 6 is 1/2. In the denominator, 3 times cosine of pi over 6 is root 3 over 2. We can eliminate the 2 in the denominator of the numerator and the denominator of the denominator, simplifying to negative 5 over 3 times root 3. So we found in step 4 the slope at the given parameter value. This problem asks us to go beyond with an application of that value. Again, note that we're working towards the normal equation. So for the slope of the normal, we want the negative inverse of the slope of the tangent. We've calculated the slope of the tangent. So we will have negative 1 over negative 5 over 3 root 3, which equals positive 3 root 3 over 5 as the slope of the normal. Now for our line equation, we need our slope as well as a point. We'll input our parameter value at point P into the original x and y equations to calculate the x and y coordinates. Looking back to the original equations, y equals 5 cosine theta. In this case, y equals 5 cosine pi over 6, which is 5 times root 3 over 2, or 5 root 3 over 2. That's our y value. And in the x equation, x equals 3 sine pi over 6, which is 3 times the sine of pi over 6 is 1/2, which equals 3 over 2. So now we have a gradient for the normal of 3 root 3 over 5. We have a y coordinate of 5 root 3 over 2. We have an x coordinate of 3 over 2. And we'll input these values into the point-slope format of the line equation. Y minus y1 equals m times x minus x1. Y minus our y value, 5 root 3 over 2, equals m, we've calculated as 3 root 3 over 5, times x minus x1. Our x1 is 3 over 2. And with some algebra, this equation simplifies to y equals 3 root 3 over 5x plus 8 root 3 over 5. Thus, the equation of the normal at the point P, where theta equals pi over 6, on the particular curve given, is y equals 3 root 3 over 5x plus 8 root 3 over 5. We've completed our requirements, and this concludes parametric differentiation example 2.